So the constants on the ground ring will stay the roots of unity, even if I change the lift of Frobenius, as I said. What I'm changing here is the lift of Frobenius on this ring, but on R, it's going to always be the same. So it depends on how you look at things, but I like to look at things as follows. So since you don't change the lift of Frobenius on R, because you cannot, because there's only one, the constants of the p derivation corresponding to it will be the roots of unity, so those don't change. What changes is the flow on GLN that you are using to construct the logarithmic derivative. But the constants are not changed because they are the roots of unity, always the roots of unity. Of course, some functions are constant with respect to some lift and are not with respect to other lifts, but that's not changing the constants, but changing the prime integrals, actually. These x's look like prime integrals here. Yeah. So you will change the prime integrals. You won't change the constants. So that's what we're going to do. Okay, so let me try to explain this. That's the next step. So I have to you want to find lifts of Frobenius, first of all, such that these ideals are preserved by the flow. But if you only want that, there are infinitely many, so you cannot pin down a lift of Frobenius like that. So that would be, not enough. So let me give some definitions here. I'm only going to concentrate on these two because SLN has another twist on it. So I don't want to... SLN is more complicated, actually. So let's just keep looking at these guys that are defined by quadratic equations. You know, SLN is defined by an equation of higher degree, the determinant. So that's going to be different, but these guys are... Okay, so let's take the matrices that define those guys, SON and SPN. They are, 0, 1, 1, 0 for the orthogonal group of even dimension. You know what? I'm going to consider just SO to R and SP to R. And I'm going to ignore SO of odd dimension. Because there's a twist there too. Yeah, these guys are crazy. So, and then these are the matrices that define, this is an R by R block, this is an R by R block. Let's take this involution, X transpose minus 1Q. This is an involution on GLN. Let's consider h of x to be x to the minus tau x. This is, of course, computable. It's x to the minus, that's q inverse x transpose qx. And you see that this is the identity if and only if x is in the group. So actually, if S is one of these groups, then S is given by the equation H equals 1. That's a connected component of that. Okay, so this is a description of these groups. And what I'm going to say is general. You can take more general involutions and do the same for those involutions, as long as the Q's have roots of unity as entries. So, but we need one more thing, a bilinear form. So-called bilinear form that defines these things. So x and y are two matrices of indeterminates, and you can consider this new matrix. So, then I'm going to give a definition. So, definition. That's the main definition. Definition of the top. Top. Important. Okay. So, so G is the GLN. And you say that phi G is, maybe it's so, if it's so important, I should use more Blackboard? Yeah, you think? Anyway, so phi G is H horizontal. Horizontal. If the following diagram is commutative, so I have G. Actually, instead of trying and failing, I'm going to just read. Because I changed the notations a number of times. So I'm going to put the PID completion on top here. You have, if you have this, the G is GLN, yeah? This diagram. H defines, of course, a map from G hat into itself, actually from G into itself. You take the PID completion, and you put phi G0, the trivial one that we looked at and it didn't work. So you want something like this. Note what happens here. If you pull back the determinants by delta, not by phi, you get 0. So if you pull them back here, you get 0. This means that if you pull back the coordinates here, which means h of x, and you apply delta, you get 0. So actually this can be rephrased by saying that the delta g, which comes with the phi g, applied to h is 0. So in other words, what you're asking is that h is a system of prime integrals for this flow. So that's h. The interpretation would be that h are the entries of this are prime integrals. Okay. Then, of course, if you take the fibers over 1, this fixes 1, so you get the ideal of the group, and hence of its connected component, is preserved by the flow. You can ask, is there only one such phi G? No. You haven't pinned down the thing yet. But first of all, it's not clear that there is such a thing. But you will see there is such a phi G. But there are too many. So you have to cut down those two. And the second condition that I'm going to impose on the phi G to cut down the possibilities to just one possibility is a mysterious one. I'm going to write it down and I'm going to try to explain it. It's very easy to explain, but it's not clear what it says. Okay, definition. Same thing as before, but now you say phi G is B symmetric if the following diagram is commutative. And again, instead of failing, I think it's okay to quote Mao. Yeah. So fail again, fail better.
On this floor, yes.
No, there's this thingy that. But this is I haven't heard Mao say it, so I'm quoting somebody who quotes Mao, who's on TV and radio and everywhere, so that's public knowledge. Okay, so this is the diagram. It's an interesting thing here. You can take this. This is the trivial one. This is the one that we're talking about. G cross G. Here you swap the two things. It's a symmetry thing. And here you have your B. It's not clear what this says. It's a diagram, it's commutative. So I said, well, one should really say that this pair is symmetric, but this was fixed anyway. And it's unique with certain properties too, so it comes from God. I can say God? Say God. Okay. So, no, you could not say God in my country.
Really?
Yeah. I mean, you could say God, but then you would be in jail.
I'm not sure you invoke both God and Mao in the same time.
Yeah, we had a different God. Yeah. So that's I will explain this, because first I found it by computing matrices until I dropped that.
Yeah.
And then I said I need an abstract definition, not my matrix stuff, because I didn't understand my matrix. And I came up with this, but I still didn't understand it. But now I understand more, so I'm going to tell you later what this means. Of course, what does it mean? So you immediately go to the Maurer-Cartan equations and try to understand if there's an analog in the usual differential geometry that this is an analog of. And there isn't, because things are different in differential geometry. SON, SPN, these are trivial things. They descend to the constants. They don't vary. So there isn't a direct analog. But this can be expressed in terms of something that's reminiscent of classical differential geometry. I'm going to say that in a second. But in any case, let me state the main theorem. So the main theorem is this. There's a unique, that's the theorem. There's a unique phi G, Yeah, so these, as I heard somebody say, connections. Yeah, these are of course flows and connections, etc. So, but they are very nonlinear. These are not linear connections. They are very nonlinear. Of course, this whole theory is very nonlinear. But they are analogs of the logarithmic derivative is of course an analog of the Maurer-Cartan connection. So that's what it is. Okay, but let's state the theorem. There is a unique phi G, which is so I'm fixing fix Q, which means fix the group SON or SPN or any other group given by an involution where Q satisfies certain properties. For instance, its entries are roots of unity and zero. So there is a unique phi G, which is H horizontal and B symmetric. H horizontal and B symmetric. Okay, once you realize that this is true, you can give it to a student and he's gonna prove it. If he's smart. So I was not that smart. I mean, it took me a while to construct it. I first constructed it using Hansel's lemma, of course, because we are all, if your name is Piatic, middle name is Piatic, then you do the. But then there is a direct way to construct it, and it's a lot of fun to play with matrices in order to construct it. So everything boils down to an exercise, an undergraduate exercise in matrices. that I haven't seen in books. Maybe it's well known, I don't know, but anyway. So that's the thing. In addition, there are some properties of this guy that come for free. Namely, if you take the normalizer of the torus, that I mentioned, the diagonal torus, and you take multiplication from the left, this is compatible with this phi, G. And also multiplication from the right by the intersection of the torus with S is compatible with phi G. This leads to a co-cycle property of the logarithmic derivative that I'm not going to write down, but restricted only to the action of the normalizer of the torus. You know this n, so once again I said it but I didn't write down, n is the normalizer of the torus. So it's the group generated by the Weil group and the torus.
And what was S again, sir?
Pardon me?
What was S?
S is one of one of the groups. Yeah. Actually, it's stronger than that. It's stronger. It's the normalizer of the torus of S. I'm going to write it like this, because this is slightly bigger, because there's a discrepancy between the Weil groups. So this is the normalizer of the maximum torus of S, diagonal torus of S, is slightly bigger than the intersection of N with S. This is the normalizer of the torus in G. So maybe I should say N is the normalizer of the torus, of the diagonal torus in the corresponding groups. So, so this leads, maybe I should write here, this leads to that co-cycle thing that I mentioned before. So this leads to a co-cycle type condition for the logarithmic derivative. Co-cycle condition for the logarithmic derivative. That's what it amounts to, actually, but the co-cycle only, the co-cycle condition only happens for when one of the two arguments is in the normalizer of the torus. This is very consistent with Tit's philosophy of the field with one element. Because maybe I should write here a remark before. This is a terrible teaching, I apologize. So, because you don't make a remark before you end the statement of a theorem, but I want to do it anyway. So the idea is that for Tits, the Weil group is, which is the permutation matrices in GLN, should be viewed as GLN of F1. This is how the field with one element started. So this was proposed by Tits. Everything started with that remark of his. Then what is this N? N has some diagonal matrices in it, but if you only take the entries with roots of unity in those diagonal matrices, so N of, this is, the second one is not Tits, but it's born from this one, and you take N of the roots of unity and 0, you should view this as GLN of F1 algebraically closed. People do that. If you ask Kontsevich, he says, sure. So people think that way. So they agree. Actually, Kotzevich suggested this. So, so this is very reasonable because the Galois group of this theory of linear equations, this theory, should live in GLN of F1 bar. Because everything, F1 bar is like the constants. So it's reasonable. This is very consistent with everything, so it's good. The second one is, I'm going to just say words, not a precise statement. There's a compatibility with with roots. In the sense that for any root, you have an additive group inside your group, and those additive groups are preserved by the flow. That's what happens. This doesn't happen in the case of SO with an odd number of dimensions. There are exceptions. The short roots are the exceptions. I asked people who are experts, what can that be? And yeah, we didn't get anywhere. Yeah, so there's an exception there. So SO3 is the first exception. Okay, but in any case, there is this nice flow. You can call this a flow. The flow gives you a Poisson condition that is compatible with the philosophy of the field with one element. It preserves the classical group in question. And I have 5 more minutes, maybe. Let me explain what the B symmetry is.
Yeah.
Because that's the weird thing. Okay. So, but I understand it now. So let me explain. Yeah.
What happens in the case of abelian variety?
In the case of abelian varieties, the funny thing is that things are much clearer.
Right. But this theorem is then...
this theorem is really...
lift in that case.
So in the case of abelian varieties, you don't have lifts.
In some cases.
You don't have... in the CM case, you have lifts, otherwise you don't. But in the case of abelian varieties, you do have an analog of the Manin map.
Mm-hmm.
So
this is really disjoint.
Disjoint, completely disjoint. Yeah, exactly. And this is supposed to be the easy case, but it is in some sense easier because abelian varieties are more complicated intrinsically. But when you try to prove the theorems about the abelian varieties, they're easier than this somehow. So at least they're easier to understand. And this is complicated by the fact that it's not commutative. That's the problem. I guess GLN is not commutative. Okay, so let me explain that remark. So explanation of B symmetry. It's actually something that rings a bell from differential geometry. So actually, for B, an element in the Lie algebra, one can define its negative. Oh, no. One can define not the negative. Let me see how I stated things. Here, just a second. Bear with me. No, you want to define an action of the involution on the Lie algebra. And what you do is you take the negative in the group law of the Lie algebra of the thing that you expect. You apply the involution to this. There will be no inverse, of course, so that's the... Okay, so that's the a formula. This is an involution on the Lie algebra. And then you take GLN plus and the GLN minus to be you know, this is actually, who is this? It's GLN, but with a funny addition. Yeah? You take GLN plus and GLN minus to be the eigenspaces of this thing. Eigenspaces. And it turns out that any B can be actually written as B plus B minus in this law uniquely. It turns out that it's, you see, this is not commutative, but it's still true. Pardon?
It's well behaved.
Yeah, it's well behaved. It's like a Cartan decomposition.
Yeah.
That's what's behind here. Cartan decomposition with respect to the involution that defines G. And then the symmetry is implies, it's not equivalent, but it implies, but that's good enough for me to understand it. So this symmetry implies that if you take an element in one of these classical groups and you try to apply the Maurer-Cartan thing to it, the logarithmic derivative, this is not going to be L delta 0. But delta 0 is the trivial one, remember, the one that we don't want. But it's going to be the plus part in the Cartan decomposition. So what you do is you take this, you Cartan decompose, and you project onto the first coordinate. That's this guy. So this is a, this symmetry is a compatibility with the Cartan decomposition. So this is a compatibility with the Cartan decomposition. Actually, it's not equivalent, as you see, but actually I have an equivalent, a version in which I have equivalence here, but this is more complicated. But it's all the same type. Okay, so yeah, that's the end of the talk. Maybe I should comment, where does this go? So what we did was we created some flows on GLN that are well behaved to each of the classical groups. For each of these flows, we have the concept of linear equation, and these flows are compatible with anything that you may hope for, but not too, you cannot hope for too much. So, but the idea is that these compatibilities are all compatible with this philosophy with the field with F1. So the next step would be to construct a Galois theory, and that can be done, and I can say a few things about this in the afternoon if there's interest in that. And also you can try to start looking at several derivations and to address the question of curvature. That's a fascinating thing for me, because just think about it. So you have for each prime, you have a p-adic world, and they should not communicate, isn't it? In the Adels, everything is a product, so there shouldn't be interactions, but actually there are.
So you have an analog of integrability conditions?
Yeah,
yes.
yeah.
But there should
Thank
be.
you. Any questions?
There should be.
Yeah.
I mean, you know, the classic theorems for called cohomology tell you.
Yeah.
Of course, and the
So there's
reciprocity
some underlying
laws and
theory that
sure.
encompasses
Yeah.
the whole thing.
Reciprocity, first of all, is one example, yeah. But it's not entirely clear how to do that.
Oh, right.
Thank you very much for your morning session.